Good afternoon. This file contains the pre-lecture notes for class on Thursday, November 7th. The relevant reading comes from our Carey textbook. These include the remaining sections that are interspersed with the previous sections you read for Tuesday's class. The takeaways from this pre-lecture are relatively simple. We'll be exploring the reactivity of benzylic carbons. Remember, benzylic carbons were introduced in Tuesday's pre-lecture. Those are carbon atoms that are bonded directly to a benzene ring. Resonance will also be an important takeaway from this pre-lecture, as the resonance around a conjugated cyclic system will determine the reactivity of the benzylic carbon. So let's begin by considering benzene ring as a substituent. Recall from last week you learned about the chemistry of allylic carbons. In this case, we have an allylic radical. Remember, an allylic carbon is any carbon that's bonded directly to a vinyl carbon. Benzyl or benzylic carbons are any carbons that are bonded directly to benzene ring. So in this case, we have a benzylic radical. Notice the similarity between the allylic radical and the benzylic radical. In both cases, we have a carbon atom that's sp2 hybridized bonded to another carbon that is sp2 hybridized. This benzylic radical can resonate into the benzene ring in exactly the same way that the allylic radical can resonate with the single pi bond that you learned about before. Due to the fact that any sp2 hybridized benzylic carbon can resonate into the benzene ring, the bond dissociation energy for any carbon-hydrogen bond in a benzylic position tends to be much lower than we would expect for a normal carbon-hydrogen bond. In fact, as you can see on this slide, the bond dissociation energy for a carbon-hydrogen bond at a benzylic position is actually lower than the bond dissociation energy for a carbon-hydrogen allylic position. The reason for this is because sp2 hybridized benzylic carbons have 4 resonance contributors, while allylic carbons have only 2 resonance contributors. Let's take a look at the resonance contributors that make up the resonance hybrid for the benzylic radical. We begin with the radical at the benzylic position. Note that it can resonate into the ring at this position, once again at this position, and again at the final and fourth position. Due to the fact that we have 4 resonance contributors, the benzylic radical is actually delocalized over the entire structure, which makes this compound quite stable. Indeed, using a reaction that you previously learned earlier in the semester, we can induce free radical chlorination at benzylic positions quite easily due to the fact that the benzylic radical is so stable. Toluene, when treated with molecular chlorine, produces selective halogenation at the benzylic position. Remember, you can also use Br2 or light or NBS to add a Br at the benzylic position if you want to place a Br instead of a Cl. Notice that this reaction is the same reaction that we've seen on multiple occasions, and indeed it should look very similar to the chlorination of the allylic carbon that we learned about last week. Benzylic positions can also undergo SN1 reactions. Recall in SN1 reactions, we first have the leaving group leave. In this case, we would create a carbocation that's at a benzylic position. Just like a benzylic radical, a benzylic carbocation has 4 resonance contributors that delocalize the plus charge over the entire ring system. As such, SN1 reactions occur much faster at benzylic halogens than they do with tertiary halogens. Compare here on this slide the relative stabilities of a benzylic carbocation with a tertiary carbocation. Notice again that the tertiary carbocation has no resonance structures, while the benzylic carbocation has 4 resonance structures. Again, the delocalization of the charge throughout the ring makes the benzylic carbocation that much more stable than even a tertiary carbocation. Notice the similarities between a benzylic carbocation and an allylic carbocation. In each case, we have an sp2 hybridized carbocation bonded to a vinyl carbon. In the case of a benzylic carbocation, however, there are additional conjugated pi bonds that permit the delocalization of the charge throughout the molecule, whereas in the allylic carbocation, it can only delocalize over 3 atoms. Let's take a look at all of the resonance contributors for the benzylic carbocation. You should anticipate that these will be the exact same resonance structures that you just saw for the benzylic radical. We begin, of course, with the carbocation on the sp2 hybridized benzyl position. We can resonate it here, down to the bottom, and one more time to produce the fourth carbocation. Once again, the delocalization of the carbocation throughout the ring in the conjugated pi system makes this carbocation much more stable than a tertiary carbocation. Here on this slide is an example of a solvolysis reaction. You already know this chemistry from earlier in the semester. Recall, in the first step of a solvolysis reaction, the leaving group leaves. This would create for us the benzylic carbocation. In the next step, the nucleophile, in this case the solvent, would attack the carbocation to produce our ether product. In this case, we selectively get the ether at the benzylic position due to the resonance stability of the benzylic carbocation. It turns out that SN2 reactions are also permitted at benzylic positions. The chemistry behind this is actually the same as the chemistry you learned around SN2 reactions of allylic positions. Like allylic halides, substitution is faster than a normal primary halide at a benzylic position. The reason for this is because the benzene ring is a flat substituent coming off of the alpha carbon. As such, it's quite easy for any nucleophile to approach the alpha carbon in order to displace the leaving group. In some sense, we can say there is almost no steric hindrance around a benzylic position. Note that benzylic positions can also eliminate just as they can substitute. Here in this case, we have the acid-catalyzed dehydration of a benzylic alcohol. Notice that the benzylic alcohol dehydrates in such a way that it extends the pi system through the conjugated double bonds out from the benzylic position to the beta carbon that's terminal. This, of course, occurs through a carbocation that is benzylic with resonance structures throughout the ring, which stabilize the carbocation intermediate to promote the elimination reaction. We can do the same reaction with a benzylic aldehyde that we just saw with a benzylic alcohol. This, of course, is an E2 elimination reaction to produce an extended conjugated pi system outside of the ring from the benzylic carbon. We can do hydrogenation reactions at benzylic positions when the benzylic position contains an alkene. Notice that in this case, we do not reduce any of the double bonds that are in the benzene ring. Remember that the aromaticity of a benzene ring makes the ring very, very stable. As such, hydrogenation reactions will not occur at any pi bond in a benzene ring with the usual catalysts that we've seen, such as the transition metal platinum. However, benzylic alkenes, which are outside of the ring, will of course hydrogenate just as any alkene you've seen before. This of course reduces the extent of the conjugated pi system back into the ring only, but the reaction will of course proceed. You can halogenate benzylic alkenes in the same way that you've halogenated any old alkene. Notice once again that the BRs add selectively to the benzylic alkene. They do not add to any of the pi bonds that are in the aromatic ring. In each case where you're faced with an alkene that's in a benzylic position, always do your addition reactions at that alkene and leave the alkenes that are in the benzene ring alone. If you add any electrophiles across the pi bonds in the benzene ring, you will destroy the aromaticity of the ring by removing one of the pi bonds. The aromaticity of the ring makes this pi system so stable that it is non-reactive. Notice here we have a hydrohalogenation of a benzylic alkene. This reaction is the same reaction you've seen before. Once again, we do not add any electrophiles across the pi bonds in the benzene ring itself because, again, this would disrupt the aromaticity of the ring. Notice that the reaction is regioselective, such that the hydrogen electrophile adds to the vinyl carbon in the benzylic alkene in order to ensure we have a benzylic carbocation, which of course is more stable than a simple secondary carbocation. As you can see here, this benzylic carbocation has resonance structures. The alternative option is to place the hydrogen atom at the benzylic carbon and the carbocation at the other side of the alkene. This would only be a secondary carbocation, which is not stable. You can do free radical addition of HBr in the same way that you've done free radical addition of HBr as well to get out the anti-Markovnikov product. Nothing new here, right? This, of course, occurs via the benzylic radical, which has more resonance structures than the primary radical that you would create were you to place the radical on the other carbon in the alkene. That being said, this has been a very quick and simple review of all of the addition reactions as well as the elimination and substitution reactions that you've already learned this semester. Of note, we simply have all of these reactions occurring at benzylic positions, which are promoted due to the planarity of the benzene ring, as well as the resonance contributors that are possible when the benzylic carbocation is sp2 hybridized or the radical is sp2 hybridized and becomes part of the conjugated pi system in the ring. No new chemistry here. Everything you've seen are reactions that have occurred with any old alkene or any old alkyl halide or alcohol that you've seen earlier in the semester. The only thing that's different is that they've been occurring at benzylic positions. We'll end the pre-lecture with two new reactions that you have not seen before. The reaction of sodium dichromate in acidic solutions will produce an oxidation reaction at a benzylic position. You do not need to know the mechanism for this reaction, but you do need to know that upon addition of Na2Cr2O7 in acidic media, you will form a carboxylic acid at a benzylic position. Note, in each case, you must have a hydrogen atom at the benzylic position for this reaction to occur. If the benzylic position is tertiary, no reaction will occur. It can be secondary, primary, or a methyl group, but it cannot be a tertiary position. Here's an example of this reaction in action. Notice the benzylic carbon at the top of p-nitrotoluene. Combined together with our sodium dichromate reagents in acidic media, we produce the carboxylic acid. Again, you don't need to know the mechanism for this reaction, you just need to know that the oxidation will occur at the benzylic carbon, and that at least one hydrogen atom must be present at the benzylic carbon for the reaction to proceed. There's one other reaction that we'll cover here at the end of the pre-lecture, which is called the Birch reduction of benzene. Notice that a Birch reduction involves sodium and ammonia. Notice we've used these reagents before to selectively reduce an alkyne to an alkene. Here we can use these same reagents in order to destroy the aromaticity of a benzene ring. We combine sodium and ammonia together in any polar protic solvent, like methanol in this case, and we remove one of the pi bonds in the benzene ring to produce instead a cyclohexadiene. Notice that the cyclohexadiene that's produced is an isolated diene. The two pi bonds that form are on opposite sides of the ring such that they have no conjugation. No further reduction is possible in this case because we no longer have an aromatic system, and of course there's no alkyne, so the reagents won't proceed. In any case where you have an asymmetric molecule, such as we see here, the Birch reduction will produce an alkyl benzene that has the most highly substituted double bond possible. Notice in each case, the cyclohexadiene that's produced always has the double bonds on each side of the ring. Make sure that your double bond always is most highly substituted and is across from the other double bond in the ring when doing a Birch reduction. With that, we will conclude this relatively short pre-lecture for next week's class. Two new reactions were introduced to you, the oxidation of a benzylic position to produce a carboxylic acid, as well as the Birch reduction, which destroys the aromaticity of a benzene ring in order to produce a cyclohexadiene. All of the other reactions that were included in this pre-lecture are simple reviews of addition, substitution, and elimination reactions you've seen previously in the semester. Of note, they all happen to occur at a benzylic position instead of your traditional alkenes or alkyl halides or alcohols. So with that, make sure to review the relative reading in your Carey textbook and come to class prepared to apply what you've learned.